Good morning, afternoon, or evening to folks tuning in from around the world. Welcome to the 126th episode of the IBM Qiskit Live Quantum Seminar Series. The seminar takes place every Friday at noon Eastern Time, and it will be hosted on this Qiskit YouTube channel. Subscribe to catch up on anything you missed, but you can only ask questions here live now during the seminar. I'm Derek Wang, a research scientist at IBM Quantum, and I'll be your host today. In just a minute, we'll be hearing a talk by Cheng-Ju or Jacob Lin on verification of measurement-induced phases without post-selection. It's a proposed solution to the difficulties of the work that Austin Minnick discussed a few seminars ago, actually. And so we'll post a link in the chat for your reference. Before we begin with introductions, let's give everyone a couple of minutes to tune in. So in the meantime, for those who are already here, as we always do, why don't you share where you're tuning in from? This seminar takes place every Friday at noon Eastern Time and is hosted here. And so in the meantime, while we're waiting for those responses, of course, there's a lot of care and effort that goes in these seminars. And so while we're waiting, I'd like to thank our producer, Zlatko Minev, video producer, Paul Searle, project manager, Zatara Darakshande, and managing producer, Olivia Lanes. All right, so I'll take a look at the chat now. There's Paul, our producer, tuning in from Portland, Oregon. Let's see if we have anyone else coming in today. There might be a little bit of lag. Okay, we have Nayo from Yokohama. We have Ron, a regular I recognize now from Chicago. Cool. Thanks all for being here. So I think it's about time that we begin. I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series. It's dedicated to you, the research and academic communities. I'm your host, Derek Wang from IBM Quantum Research, and today I have the pleasure of hosting Jacob Lin, who will be speaking about verification of measurement-induced phases without post-selection. Dr. Jacob Lin is an RQS postdoctoral fellow at the University of Maryland. And before going to UMD, he was a postdoctoral researcher at the Perimeter Institute from 2019 to 2022. He received his PhD in physics from Caltech in 2019, and his research interests lie at the intersection of many-body physics and quantum classical simulation. More specifically, he's interested in quantum dynamics and closed and open systems, thermalization and chaos, and the lack thereof in quantum many-body systems. Take it away, Jacob.
Yes, thank you, Derek, for the kind introduction. And hi, everyone. My name is Cheng-Ju Lin, and then I usually go by Jacob. So today I'm going to tell you some the story that that we've been developing for quite a while about this verification of measurement-induced phase transitions without post-selections. So hopefully that we can post our results like in the next few weeks. So it's basically ready. It's just lack of some of the final touch that we're trying to polish our work. So and this work is done in collaboration with Hossein and Nico, and both are postdocs at UMD, and then we're both affiliated with JQ and Quick at UMD, and also the PI is Professor Muhammad Hafizi. Yeah, and this work is mainly funded by this NSF funding through this robust quantum simulation funding. Yes. So as Derek mentioned, that my research interest is actually lie in this intersection of the many-body physics or condensed matter physics and this recent development of these quantum devices or quantum information. So something that kind of attracted a lot of the attention for the condensed matter physicists is actually this so-called measurement-induced phase transition. And then so I know there's actually a lot of different backgrounds of the audiences. So what I will do is that I will try to give a hopefully high level and clear introduction of this phenomenon that people recently are so excited about, this measurement-induced phase transition, and especially that I will introduce the model that what kind of model that people are starting to show that has this phenomenon. And especially something that I want to point out, and also as Derek mentioned, is that to probe this kind of phenomenon in any kind of quantum devices, there's actually something seemingly fundamentally hard to do this. And this is what people call the post-selection barrier. And then I will explain like what is this difficulty. And then after introducing the model, the phenomenon, and also the challenges, I will mention what kind of proposal that we're trying to propose to overcome this post-selection barrier. So shortly speaking is that instead of looking at the quantum wave function coming out of your quantum device, we look at the mid-circuit measurement outcome. And then we want to ask that, can we just look at this mid-circuit measurement outcome and then doing some kind of classical post-processing so that we know what kind of phase that this quantum device is in. And then after introduce this proposal, and then what kind of classical post-processing that we can do, and I will apply our protocol to the following models, and then which I will, of course, try to explain this more clearly. And then in the end, I will try to discuss some of the result and implication of our proposal. And of course, that if you have any questions that don't, if you just feel free to type in the chat, and then I guess Derek will like interrupt me and then just ask me the question, and hopefully that I can explain things, and then everybody can learn more and then have some fun here. Yeah. Okay. So we know that one of the main thing that why people are, it's like people working so hard trying to make a quantum device or a quantum computer is that just because quantum mechanics is hard to calculate classically. And what does it mean by hard? Meaning that to do quantum mechanics, that if you have n qubits, then you're basically doing a linear algebra with a 2 to the n dimension of the linear space. And so the resource that you need to use to do any kind of quantum mechanical calculation will quickly run out if you're only using classical computer. So that's why a quantum computer or a quantum device might seems like a good idea if you want to calculate quantum mechanics. So especially that if you it seems to be natural that if you can have a device that just simulate the quantum mechanics directly, then this seems to be like a very straightforward way to demonstrate the so-called quantum advantage, right? Even though, okay, so and actually this is like the approach that like the research group in Google that they use, that you just have a whole bunch of qubits, and then you just operate some quantum evolution operation, and then you just try to show that, oh, this kind of calculation that the classical computers are intractable, they cannot do that efficiently. So and when you talk about the quantum devices or this quantum or quantum computer, usually the model that you think about is that, okay, I have a whole bunch of qubits, and then what I need to do is that I can operate some unitary gates between any two qubits, right? So this is like the circuit model that when you're thinking about how to carry out the quantum computation, this is kind of like the model that you use. And this is also starting to become like a toy for the condensed matter physicists. So and also just to set the stage of the model, that right now I'll be specific. So right now I'm considering the quantum device that you can run this type of the quantum circuit that say you just prepare your initial state is some product state. Let's say I just initialize all the qubit at zero state. And then I consider the quantum circuit that's in this brickwork structure, meaning that at each layer that I will operate a unitary gate between like the neighboring two qubits. And then I operate this in this brick wall fashion. And each rectangular represent a unitary gate that I just draw from some random ensemble independently. So for example, like most of the popular choices, maybe say the unitary is drawing from some hard random ensemble, meaning that this if you write it as a matrix, that it's drawing from some u to the 4 random matrix ensemble. And there is also another very special type of the ensemble people like to use. It's called the Clifford ensemble, because this kind of circuit will you can actually in fact simulate this efficiently on the classical computer. So what us condensed matter physicists do is that okay, in this quantum computation model, not only this circuit model, not only you can do the unitary operation on the qubits, what you can also do is actually you can also do the measurement, right? So so now we modify this random circuit model a little bit, and then some people call this like the monitored random circuit model or the hybrid circuit model, meaning that in addition to this brickwork unitary structure, brickwork structure that each rectangular representing a unitary gate, between the layers of the unitary gates, I can actually do some projective measurement of each qubit, and especially that I will consider that this measurement process occurred randomly, meaning that after each layer of the unitary gates, for each qubit, I have a probability Qn. And sorry, I guess you guys cannot see my cursor, but at the bottom line of the sentence, that at each layer, that each qubit has a probability Pn that this measurement process occurs. And then that here that I represent this measurement process as this yellow diamond. And then if you write the measurement process as this cross operator representation, and this looks like this. And in particular, let's just simplify the problem. Let's say if we have a qubit, and then we can just measure that in the z basis or computational basis, so that you will get the outcome is either 0 or 1. Okay. And also just to set the notation that I will just collect all these unitary gates as a list of this curly U, and then all the locations of the measurement, I will just collect them, denote them as this curly X. And also that the collection of this U and X defines a circuit that I just collectively denote that this as C. So as I mentioned, that if we draw the random unitary from some random unitary gate from some ensemble, and also determine the measurement location randomly through this random process, then for each circuit that there is a probability distribution that we can determine this structure that's coming out of some probability distribution that we know. Okay, so now that after we specify the circuit, let's think like what happens if we want to run this circuit architecture on a quantum device, and what does the quantum mechanics say? So the quantum mechanics say will say that okay, let's say we start out with the initial state, that's this all 0, and then represented by psi naught here. If you look at this circuit diagram below the circuit diagram, that there's a wave function. So starting out with psi naught, the first layer of the gate that I denoted as this U1, so you will get this wave function. But once you hit the measurement, what happens is that depending on your measurement outcomes, let's say if you turns out that the quantum mechanics will after the measurement that that qubit will be projected into either 0 or 1, then mathematically that you will operate this cross operator on top of the this wave function. But you actually have to normalize that. So before normalization, that you will have this psi tilde wave function, and then that's called normalized. So and then quantum mechanics actually tells you that the probability of that outcome to happen will be calculated by the norm of this normalized wave function psi tilde. And then the wave function after you measure the qubit will be the normalized wave function. That's this psi. So and then what you can think of this measurement process, that if you, instead of only one measurement, if you have a lot of the measurement, so each measurement, let's say you can have a possibility of 0 and 1 outcome, right? You will have 2 possible pure wave functions depending on the measurement outcome. And then let's say after you do 10 times of the measurement, there will be, say, 2 to the 10 different possible so-called trajectory wave function. Each one is denoted by this mid-circuit measurement outcome string, and then each one will have a probability to occur given by this function probability Pn condition on the circuit C, and also the outcome of the wave function that you have to normalize that. Okay, so this is actually what one way to think about what happens in quantum mechanically, that you have a unitary operation, you measure things, and then these wave functions start branch out. So in the end, that you have an ensemble of this pure wave function, that each wave function is denoted by the measurement outcome. So so what's interesting about this model is that people numerically discover that there's this phenomenon called the measurement-induced phase transition. So let's consider some special limits. So first, let's consider that if I don't do any measurement at all, so right now I just have a wave function, and then I just operate this random unitary gates in some brick wall fashion. And then I can imagine that if I run the circuit deep enough, then the final wave function will basically looks like a random wave function that you just draw from this to the n Hilbert space, and then n is the number of the qubits. And there's actually a famous result saying that, oh, if you have like a random wave function in 2 to the n Hilbert space, then if we look at the entanglement entropy, so this is the S of rho here, and then the entanglement entropy of the subsystem denoted by this rho A, then you will actually see this entanglement entropy scales as the size of this subregion A, basically linearly. So schematically, that's represented by this red line, and then that's this schematically represented by this blue line, and then represented by this blue dots if you don't do any measurement. But and then there's another limit that's denoted by this green line, meaning that if the measurement probability is 1, so after each round of the rectangular unitary gates, I just measure any qubits. So whatever of the outcome wave function that you have, you will just always have a product state. That's product state, and then with the qubit in the configuration of this of the measurement outcome that you specify. So if you calculate the entanglement entropy for every wave function, every trajectory wave function, you know every trajectory wave function is just a product state. So the entanglement entropy of that should be 0. Or if you look at the scaling of the subsystem size, it's just always 0. That always stays in constant, right? So and this entanglement phase transition phenomenon is that, okay, now let's suppose that instead of this special limit, if I say instead of 0 measurement rate, I just measure this just a little bit more, what happens? And then people discover is that for this each trajectory wave function, if again that you calculate the entanglement entropy, and then you average over all the these trajectory wave functions, and by average I mean weighted by the probability of getting this trajectory wave function, denoted by this over bar here. Then what you will see is that if your measurement rate is low enough, then you will actually see this averaged entanglement entropy scaled still as like a volume law as a function of the subsystem size. But if you measure your system with a high enough rate, then actually your this averaged entanglement entropy will scale as a constant or so-called so-called area law as a function of the subsystem size. And what's interesting is that there is a critical point, meaning that there's a critical measurement rate that separates these two volume law and area law phases. And then at this critical measurement rate, that the entanglement scaling will look like a logarithmic as a function of the subsystem size. Okay, so so this is basically the phenomenon of the measurement-induced entanglement transition that that actually shows up in this type of the monitored random circuit, that you have a random brick wall structure, and then you just measure things in between randomly. Yeah, and also maybe this phenomenon is initiated by these few of the works that there's actually so many works that that's working on this field, but here that I'm just mentioning some of the first few groups that their work that they try to push this thing. Yeah. Sorry, is there a question or?
No, just commenting. That was really helpful. That was a really nice pedagogical explanation of this, very complicated phenomenon. So thanks for that.
Okay, thanks. Yeah, and of course, again, like for the audience, if you have any questions, just feel free to ask. Yeah. Okay. And as I mentioned that you can then like as condensed matter physicists are starting to add more ingredients. So this is like the version that without any structure, or the structure is just this unitary gates and then the random measurement. But one thing that physicists like to do is that to introduce symmetries. So what happens is that if you introduce more symmetries, for example, like if your random unitary gates having some special structure that's dictated by some of the symmetries, and also the measurement or the type of the measurement that you can do has to obey some kind of symmetries that you impose into the quantum circuit, that not only that the system will show this entanglement transition phenomenon, the system can even show some so-called order disorder phenomenon. So for example, like one example that is this so-called charge sharpening phenomenon. So this is the type of the circuit that if your circuit also has the so-called charge conservation law, and this conservation law meaning that sum over sigma z on all the qubits is a constant or commute with all the unitary gates in the measurement process, then actually not only the entanglement for each trajectory will show this entanglement phase transition. If you look at the charge fluctuation of each trajectory, that they will also show different behavior depending on the measurement rate. And also there are different type of the symmetry. For example, like this Ising symmetry case, that if your circuit, the unitary and the measurement have to obey some kind of so-called Ising symmetry, then each trajectory wave function, depending on how frequent that you measure some of the observable, the trajectory can show some kind of quote unquote so-called spin glass phase, and then that's some kind of Ising symmetry breaking phase. So this is like one example of the this kind of system can show some order disorder phase. And another example that is actually, if you have this D2 cross D2 symmetry, you can even have this trajectory wave function that shows some symmetry protected topological phase. Yeah. So just to show you that, there's actually a lot of rich things that one can have by introducing the symmetry. And so as I mentioned that, okay, these are just some toys and the condensed matter physics that they're playing with, and then all these phenomena were observed initially mostly coming from the numerical simulation, and then that's something that you did on your classical computer. But can we, this is seems like a pretty natural circuit model that you should be able to execute on your quantum device or quantum computer, right? So can we probe this? Has people done this? And yes, so for example, like actually the very beginning of maybe the experimental work is actually done by this done on the ion trap computer, and it's actually done by the local collaboration in the UMD. Yeah. So what they could do is that they realized this phase, and then they did this up to like 8 qubits or like around that number. Yeah. And also they're slightly different setting, but it's morally the same kind of phase transition. So recently, like as Derek mentioned that a few seminar series ago, that the group from Caltech, like Austin Minnick's group, that they also tried to realize this phenomenon of the measurement-induced phase transition and on the IBM quantum computer. And I think what they did is that they did like maybe 8 qubits with a relatively slightly deeper circuit, and they have some data that they use like 14 qubits, but I think that they could only do some short, shallow, like relatively shallow circuit with not too many measurements. So just for some dramatic effect, that they reported that they used the IBM device, and then the calculation took like 32,000 qubit hours. And then of course that they're probably not like so just for the dramatic effect, that if I calculate this many qubit hours that they're using, and then if they are just paying like the IBM device pricing, like this pay as you go playing, I guess the price is like a second for $1.6, and then you actually calculate get like to run this experiment that you actually pay like almost $200 million. And of course, I believe that they're not really paying this much, but this is just to show you that how expensive it is to realize and probe this phenomenon on a quantum device. And you could like even just for 8 qubits or 14 qubits. So you may ask like, why is it so expensive? Like, is it because there's a lot of noise in the device that you somehow have to correct that? And actually, that of course that's one of the factors. For example, like in Austin Minnick, that their experiment that they have to use a lot of this error mitigation technique, and then that's actually quite expensive in terms of the number of qubits. But actually, this phenomenon, there's a seemingly fundamental challenge to probe this thing on the quantum device. This is this so-called post-election barrier. So if you recall this more carefully, that the way that we just described to see this entanglement phase transition is that you have to have each quantum trajectory wave function, and then this quantum trajectory wave function is from your quantum device, but then you have to be able to measure or calculate or probe the entanglement of this each trajectory wave function. But to get this each trajectory wave functions, there are probably different protocols to, if I give you a quantum wave function, how do you measure the entanglement entropy? So maybe the most naive way is just that you do some quantum state tomography that really know what is this wave function, what is this wave function, and then you just use the full information of this wave function to calculate the entanglement entropy. So this is like the first expensive resource that is that to get this tomography, you actually have to prepare the same state basically exponentially many times to have a good quality of the result. But there's another issue is that again, you see that now you need to do the tomography for this individual trajectory wave function, which you get from this series of the measurement. But to get exactly the same trajectory wave function, you have to repeat the experiment, but only having the result of the wave function that all this mid-circuit measurement outcome are exactly the same, right? So for example, like if you want to measure this entanglement or do the tomography of this trajectory wave function denoted by the outcome of all zero, of all the measurement that will give you zero, you run the circuit again. You run the circuit again. It's very likely that you'll get some measurement outcome that's not all zero. And then you can see that if each measurement gives you a probability of having an outcome, even let's say just 1/2. If you have 10 measurement process to get the probability of getting the same outcome result is like 2 to the -10, right? So you see that the probability of getting exactly the same wave function is actually exponentially small in the number of the measurement that you need to do. So actually, this is what so-called the post-selection barrier, and then I believe this is like the fundamental challenge that Austin Minnick they proposed maybe a few seminar series ago. Like it seems like there's to probe this thing on a quantum device that you just have to prepare multiple copies, and then it seems like there's just no way to overcome this post-selection barrier. Yeah. And the situation is actually different that if what you want to probe is this usual observable. So if we look at the line here that trace row O, if this is only the thing that you want to measure, then there's actually no this post-selection problem. So you can have an example of this trajectory wave function, and then every time that I give you a trajectory wave function, I measure something, say measure sigma z, I get a value, and then I just repeat it for whatever of the trajectory wave function that I have. But I average over this thing will just gives me back to this trace row O. So if this is the thing that you want to measure, then there's no post-selection problem. But the crux of this measurement-induced phase transition phenomenon is that this total density matrix of rho doesn't show any singular behavior. It's essentially just a maximally mixed state. It's really that this trajectory wave function, the property of that you have to probe to see this phenomenon. Yeah. So right, I'll just pause for like maybe 10 seconds, and then so that was like an introduction of this measurement-induced phase transition, and also the model, and also the post-selection barrier, and hopefully that I already set the stage, like what's the challenge of probing this thing on a quantum device. Okay.
Great. Yeah, I don't see any comments there. And maybe this is jumping the gun a little bit, but this classical post-processing you're going to propose will be to detect the phase, right? To detect whether you're in one phase or not. And I'm wondering if this process allows you to find other things about those phases, or is it like very hyper-specific for just detecting what phase you're in? But if you want to get some other property of the phase, would this method not work? This is probably something
so what do you mean by other properties of the phase?
So maybe this is something that I should wait till later, but it
Yeah.
seems that at some point you'll have to diagnose like the scaling of the entanglement entropy, right?
Oh, yeah. Actually, in principle, we can do that, and then actually, you will probably show in the later slides that we actually try to do this. Yeah. Okay. So, and let's think more carefully. How could this challenge even be avoided? So, one key point is that it was actually like some question asked by Muhammad Hafazi, like kind of it was like a surprising development that coming out of his question. So you see, like the way you would think that to do this is that okay, I have a quantum device, and then in the very end, after I do this random gaze and then the measurement, I get this final wave function, right? And of course, that to know everything about this measurement-induced phases, that I should probe this quantum wave function, right? So it seems natural. But actually, there's another information coming out of the quantum device that you actually didn't use. That is actually this mid-circuit measurement outcome. So every time you run this circuit, you know where you did the measurement, you know what are the outcomes. So Muhammad was asking, like, okay, is there any way that you can just look at this measurement outcome and then just to know what phases that you're in? Okay, so and maybe to frame this more carefully, what it really means is that okay, let's say I run this circuit NC times. So for this NC times that I sample different unitary gates, different measurement location, and also the measurement outcome, can I use the measurement, this information of the measurement outcome and also the location of that, doing some kind of classical calculation, meaning that can I find a function W that only depending on this measurement location and the measurement outcome, such that for each result the quantum device sent me, I do some classical calculation. That's what I call the classical post-processing. And then each run, I calculate this W, and then now I have NC of this W, and then I just take the average of that. And then can I use this quantity to know what phase, what this measurement-induced phase is that the quantum simulator is in? So that was like the question we're asking. Okay, and also just a notation that when I have an over bar, that just means that I'm averaging over this quantity with respect to the measurement outcome, measurement location, and also the random unitary gates. Okay. So now this is the question: is there such W exists? And turns out there's actually some trivial options that you can write now. So for example, like one option is this Wn that let's maybe look this more carefully. So in the denominator that I have this probability P n condition on the circuit multiplies the entanglement S with this trajectory wave function. But here in the numerator that instead of averaging over all the measurement outcome and all the measurement locations, I only average over the random unitary gates. And also the denominator also having the same property. So you can see that the only leftover variables that, or this W will depending on is only the measurement location and the measurement outcome. So if you plug this back into this over line that's averaging over U, X, and N, then you indeed get back to this average entanglement entropy that you have. So technically there is actually this classical function that you can do post processing with, and that actually gives back to you back to the quantity that you want. But some of the problem is that okay, now you do have a quantity, right? You want to calculate this using your classical computer. The problem is that when you look at this, it seems like it's kind of hard to calculate, and especially it looks like the only way to calculate this thing is as if that you're just run the simulation on your classical computer. So, and especially when the unitary gates are from some hard ensemble, we know that you just cannot do this efficiently using a classical computer. And also averaging over U, also average over U. If you look at the numerator, this might be a little bit hard to explain, but what happens is that the things that you're trying to average with over U is not just a simple polynomial function of U. So there's exists this result called the Weingarten formula, meaning that if the something that you want to average over the hard random unitary gate, if it's only some polynomial function as a u, then you can actually having some analytical result of this average. But because of the numerator is actually something that's fairly complicated in you cannot invoke this Weingarten formula to simplify your calculation, and that's what I mean that this W, even though you can formally write now, but you just it's very hard to calculate this on a classical computer. Okay, even though it can do the job. So that's why we kind of try to opt for a little bit different choice of the W. So this is like the protocol that we propose to probe this entanglement phase transition. So instead of just one number W, we propose that every time that you give me this measurement outcome and the location, I want to calculate two numbers. One is this W1, the other is W0. And then after I calculate these two numbers, I average over all the circuit runs, and then I take the ratio of them. So this is this W1 average divided by W0 average. And then I also take log 2 of that thing. So this quantity, let us call this like some kind of generalized entropy. So, and this is actually the quantity that we use to like as a proxy for this entanglement phase transition. And if we look at this W1 and W0 more carefully, so again, like you see that the denominator is the same as the previously proposed WMX here in the top of the slides, but the numerators are a little bit different. So the reason why we design the numerator in this way is so that we can use this Weingarten formula to simplify the average of the average over U. So that's actually the main reason why we kind of modify this W in this way. And also, actually, this quantity has been studied in the previous theoretical work, and especially that a lot of the condensed matter physicists that they try to understand this measurement-induced phase transition phenomenon. So what usually they do is that there's this. Sorry, this might get into too specialized or too technical, but I'm just gonna mention this real quick that people use this so-called replica trick. So after you do this replica trick, and that's essentially this this log 2 p n condition on c to the r minus 1, this formula in the bottom part of the slides, right? So after you do this replica mapping, the quantity inside the log can actually be mapped into a statistical mechanics model. And then you can use this statistical mechanics model to understand what does it mean in the area law and the volume law phase. And then if you are able to take this so-called replica limit, meaning that this R goes to one limit, then you actually recover this average entanglement that you wanna probe. But here that we cannot do this replica limit, at least not easily. So we're basically calculating this replica version of the generalized entropy, which corresponding to R equals to 2. And just a caveat that usually these two quantities, even though that they both can tell you that there's a volume law to area law phase transition, and usually the critical point will be different, and also the critical property will be different. Yeah.
Okay. Sorry.
Yes.
Can we take a pause at this slide here? So I guess I can see how you ended up at this expression, maybe like iteratively based on the requirements of this measure that you wanted in the first place, right?
Yeah.
Now that we have this, maybe you help me synthesize in a way to understand, like what is it generalizing overall? What is it generalizing to? And then how do we understand this general measure, like how, or this general measure of something, how does it, in what situations would it differ from like a more standard situation that one might have more physical intuition?
Yeah. So, yeah, actually, that's a great question. So maybe one way to see what this generalized entropy is actually if you look more carefully. So if you look at the right bottom part of the slides, that you see that there's like a p prime n that with a grayish color of the formula. So what actually seems my like not so rigorous way trying to understand this generalized quantities that you see that without taking the average over U, and then let's look at the quantity, that's this W1 divided by W0. If you don't take average over the U, but you sum over all the measurement outcome instead, so what is essentially kind of doing is that you're weighting this trace Roway square as of n with this new p prime probability distribution. Okay, so to get like the original result, you want to weight this trace Roway square n to p of n to the power 1. But here now, instead of weighting this to the power 1, you weight this to a modified or skewed probability distribution that's p to the power 2, and also with a normalization factor that's calculated from this W0. So actually, that's why this replica trick, essentially what it does is that it kind of modifies this averaging quantity. Instead of weighting with probability to the power 1, it's weighting to the probability to the power r, and then normalize with and then normalize that. So this is kind of like the some of the idea, or maybe my understanding of how these generalized quantities that's related to this ordinary quantity that we want to look for. Right. I don't know if that answers the question.
Oh, that's helpful. Yeah, thank you.
Yeah. Okay. Thanks. Yeah. Okay. Right. So okay. So just to recap. So now the protocol that we are proposing is that after you run the quantum device, you don't look at the quantum wave function. Instead, you look at the mid-circuit measurement outcome. And then if I take this mid-circuit measurement outcome, I want to do this classical post-processing, meaning I want to calculate this W1 and W0. And then in the end, that I use this data to calculate this generalized entropy S2. Yeah. And also just as a backend, like what kind of classical calculation that we did to do this post-processing, that we use some. So it turns out that this classical post-processing, this W1 and W2, can be mapped into a tensor network contraction problem, so that we develop some kind of matrix product state algorithm to carry out this post-processing. And that we'll get into more detail. But if you heard about this matrix product state or tensor network, then that's basically the method that we use for the classical calculation. Yeah. Okay. And also, not only the entanglement phase transition, if the system that, as we mentioned, that if you have some symmetries and then they have some order disorder transition, then we can actually also modify our protocols to detect this order disorder transition. So it will be probably more clear that when later that I apply to a more specific model, like what kind of post-processing function that we choose to detect this thing. Okay, so and also I kind of want to mention that so my title is like verification of measurement-induced phases. Then so why do I call this verification? So if you're really coming more from the quantum computer side, like if you're real quantum computation, like I don't know, computer scientists, then this protocol is kind of analogous to this task of classical verification of quantum simulation. What it means is that you run, there's a prover, meaning now this is the quantum device. The prover, after you execute this quantum simulation, you do some kind of measurement in this quantum device, and then you get this classical data. And now you send this classical data to the verifier, and then the verifier only has the capability of doing classical calculation. What kind of classical calculation this verifier or the classical computer can do to verify that the quantum device is doing the things that we expect that it to do. So this is like a analogous protocol to that kind of situation, but here that instead of really verifying, here that we're just using this classical data out of the quantum simulator after the post-processing that we try to know, like having this quote unquote order parameter to know what is the quantum simulator doing. And this actually is very similar to this cross entropy benchmark that say the Google team that they were doing. So basically what they did is that they also kind of, it's analogous to the protocol that we propose here. So after they run the quantum circuit, they do the measurement in the last round. And now you have a classical computer according to the the random gates that you use and also the measurement outcome, you can calculate the probability. And then what they do is that they weight this probability. So the W for them is the probability of getting this outcome. And also in their case, that they also need to use the information of exactly what unitary gates that you operated. But here for us, that we don't care as long as you tell me what kind of ensemble that you're using. And actually, there's also a work that kind of following the same idea, that they use this cross entropy benchmark idea to also try to verify, also try to probe this measurement-induced phase transition phenomenon without the post-election. So but for them, that they're focusing on the case that when the unitary is coming from a Clifford ensemble, and also for their protocol, they also need to use the information of the gates explicitly. Yeah. Okay. So right. So hopefully that these are like clear enough, like the protocol. So in the last like 10 minutes, I'll show like how we apply this protocol doing the numerical experiment to see if we can actually indeed like see this phase transition after this classical post processing. Yeah. Okay. So right, the first example is this most original example of the quantum circuit, meaning that we do this brick wall structure, and then after each layer of the gate, we do the measurement with the probability Pn for each qubit, and then the unitary gate U, here we consider that it's drawing from this hard random ensemble for qubits, and then so D equals 2 will be the qubit. Yeah. So again, just to recap, we run the quantum simulator NC times, and because I don't really have the access for the real quantum device, so here that anything when I say that it's from the quantum simulator, what really happens is that I just use my classical computer to simulate the quantum mechanics, and then as if that I'm really doing this quantum simulation experiment. Okay, I'll still code that.
Quick clarification. So those measurements in yellow there, do you fix their locations? And so is that a probabilistic measurement, or is even the location itself of these yellow diamonds, or is that like a deterministic measurement, but their locations are probabilistically placed?
It's a projective measurement. So let's say that I always measure sigma z basis, but the locations are random. Yeah. So the locations are determined that it's basically each one has a probability of PM to be measured. So let's say if I have two qubits, then the probability of both measure is like PM squared, and then one. So basically,
so like what we're looking at here in the left is like one sampling of this circuit.
Exactly.
Yeah.
Exactly.
Okay.
Yeah.
Thank you.
Exactly. Yeah. Thanks for the help for the clarify. So yeah, this is like one sampling. So this NC times, not only that we sample through the unitary gates and also the measurement location, and then after running the circuit, that we will also get the outcome. So this NC times, this NC runs include the sampling with the outcome, the unitary gate, and also the measurement locations. Yeah. And again, that after running the circuit, each sample, that I will get the result of the measurement outcome and the location. I use this location, and then I use a classical computer to do this post-processing to calculate W1 and W0, take the average of that, take the ratio, and take the log to get this generalized entropy S2. Okay. So, sorry, maybe I'll get to skip this technical slides, but again, that really the backend how we calculate this post-processing calculation is that we do some kind of tensor network contraction, and then it actually is gonna get more too technical, but I'll just show you some pictures that we can actually do that, and then we come up with some kind of MPS MPO algorithm of matrix product state, matrix product operator algorithm to carry this calculation. Yeah. So so here's like a result. So the solid lines here. Okay, here that I'm showing the result of this generalized entropy at the subsystem size. That's half of the total system size. And then here that I show the data with total system size 8, 12, 4, 8, 12, 16, and 20. And then the solid lines are using this quote-unquote verification protocol that we just proposed. And the dashed lines are the result that really coming from the quantum simulator, quote-unquote quantum simulator. In reality, it's the classical simulation that we did. And one can see that, oh, indeed, that not only that they do agree with the real supposedly the quantum simulation results fairly well. And you see that we can indeed see that at low enough measurement rate that it looks like a area law scaling, while at high enough measurement rate that we have a entanglement, quote unquote entanglement scaling that's like area law in the substituted size. Okay. But there are actually some remarks that I want to make for this particular situation. The first is that if you recall that this is kind of like the result that we have two replica copies, meaning that when we do the average over U, effectively that U, this unitary U will appear twice times the U dagger version of that. So if you know there's this result called the design, then actually random Clifford gates form T design and then T is 3. So which means that this result that we show here will technically be identical to the quantum circuit that if the random unitary U's are coming from a random Clifford circuit. So so meaning that if you're really a quantum computer scientist, that you really like this verification kind of the context, that which means that you can spoof this verification process, meaning that instead of really having a quantum simulator, I could actually calculate things just using Clifford gates and then still give you these outcomes that, and then after your verification, that you'll get this exactly the same result. Yeah. So, but that's fine. But if for our purpose, that we just want to see the numbers and then see the scaling, that actually this is okay. And also that if this thing is kind of specialized, that if you only consider qubit, and actually the algorithm that we use is actually general qubit for hard gates. That so there might be some cases that this is not really a problem. But I would say but actually there's a more probably serious bug in this protocol for this particular case is that it turns out that because of the hard random average is too strong, so this post-processing, this W function that we calculate, instead of depending on both the measurement outcome and the measurement location, it will only depending on the measurement location only. So whatever outcome that you get is actually not important. So shortly speaking is that if you have, say, an outcome 0, then to get another outcome, then there's a unitary that you can relate the outcome 0 and then the outcome 1. But this unitary V can always be absorbed into this hard random ensemble, and due to the property that this hard random ensemble is invariant under any left or right unitary transformation, so you basically get a result that it's independent of the outcome, it depending on the locations only. But why would this be a problem? Because if you look at we technically want to average over all the outcome, all the gates, and all the location. But now if if it's independent of the outcome, then you average over the outcome. Then you're essentially only sampling with the averaging over the unitary gate and then the location of the measurement. And both are the things that you have classical control. The only thing you don't have a classical control is actually the measurement outcome condition on the circuit. So even though technically that this protocol will still work, but the quantum simulator part is actually redundant, because what you need the quantum simulator for is really that you generate this outcome sampling according to the probability distribution P of n condition on the circuit. Okay, so this is kind of like a bug for our protocol in this particular case. But I also want to mention that as I mentioned, that there's this cross entropy benchmark protocol for the measurement-induced phases, and then this seems to be like a general bug if the unitary gate is also from Clifford. So in that case, that the classical post-processing from their protocol also will not depending on the outcome. It will depending on the unitary gate and the locations only. So in that case, that the quantum simulator part seems to be redundant. Yeah. So one possibility that this bug can turn into a feature is that, if instead of the measurement, if this X is like some error, and especially that if you are considered like the type of the error that you know where's the location, then now this P of X, you don't have a control that now you really need to use quantum simulator to detect this P of X. Then this could be like a bug, but this is a little bit like too specialized. Okay, so then, okay, now we know that in this original version of the scenario, even though the verification protocol technically would work, but the quantum simulator part becomes redundant. What would be the occasion that the quantum simulator part will be essential? So the case is that we don't make the random unitary gates too strong, such that it washes out any measurement outcome. So one way to get around this is that if your unitary gates have some structure, so that's why I mentioned that there's also this result that if you impose some symmetries in your random monitor circuit model. So for example, like the next example that we use to test our protocol is this so-called this hard random unitary circuit, but with a charge conservation. So basically, it's still the same circuit architecture, but right now the unitary gate, instead of drawing from this U to the 4 random unitary matrix, it's drawing. It has this structure that in the 0, 0 entry that it's just a phase exponential I phi naught, and then phi naught is just a random number from 0 to 2 pi. And then in the entry of 1, 1, that it's just a number exponential I phi 1, and then phi 1 is again just some random number from 0 to 2 pi, which are independent of the phi naught. And then in the middle of the entry, that's 0, 1, and 1, 0, that you just have a matrix that's drawing randomly from a U2 unitary matrix. So this is this type of the model that has this charge conservation law was studied intensively in this paper that on the top of the slide. Okay, so now because of the structure of the unitary, this W function, the post-processing result will actually depending on the measurement outcome. So the quantum simulator part is really essential here, right? Because in principle that we expect that this P of M condition on C will be hard to get the measurement outcome sample from this distribution from a classical computer. Yeah. Okay, and again, like in the backend that we just mapped this classical post-processing as some kind of tensor network contraction, and it's just some figure that to show you how we could be able to do this. And here is just the result. And you see on the left-hand side, again, that we are measuring this generalized entropy. At a low enough measurement rate, say 0.05, you do see that we here that I show total system size 16. And then you see that at low, small L, that the entanglement entropy does seem to scale like linearly. But while your measurement rate is high enough, say 0.2, then the overall shape of the entanglement entropy seems to decrease and then looks like an area law. And we could even try to perform some kind of scaling analysis, trying to extract some of the critical point and the critical data. Here that this PC and mu are the numbers that we got. And again, I have to emphasize that in general that this S2 will shift the critical point if compared to the older parameter if you use like the averaged entanglement entropy. Yeah. Okay. So, and also like as I mentioned that now there are some of the older parameter or like the phases other than the entanglement phases that one has. For example, here that one thing like this original charge sharpening paper that they propose is that if you look at the charge fluctuation of each trajectory wave function, then you'll see that at high enough measurement rate that the charge fluctuation is basically 0, but while at low enough measurement rate that there's still some finite charge fluctuation. And here that again that we cannot calculate the average of charge fluctuation with respect to all the trajectory, we have to use this like replica or modified version of that. But you can still see that the dashed lines are the data I got from the quote-unquote exact quantum simulation. And then the solid lines are the ones that we got from our protocol. And we do see that they does seem to track quite well with each other. Even though L equals to 18 might be some discrepancy, but that's just because I think we don't have, I only run like 1,000 sampling, and it could be improved if I increase the sample run. Yeah. So finally, I want to mention is that the last example is that if you impose a Z2 symmetry in your circuit, then as I mentioned that you can have this easing symmetry breaking or like a spin glass phase in the trajectory wave function. So the cleaver version of this thing was studied by Cheng-Ju and team in this paper that I cited in the top of the top of the slide. So right now we consider the circuit structure slightly different. So now each rectangular can either be a unitary gate that drawing from this ensemble. So basically it's blocked like has this block structure, and then each V2 and U2 has are drawing from a 2x2 random unitary matrix independently. So we have a 0.2 probability for each rectangular to operate the unitary gate. But then there's a 0.8 probability that it does the measurement. And if it does the measurement, that we have two scenarios. One is that there's a 0.2 probability to do ZI measurement, meaning that then you have a 0.8 probability to do XX measurement. And then another scenario is that another case is that you only have 0.8 to do ZI measurement and XX measurement that has the probability 0.2. So the upshot is that if you have high enough XX measurement rate, then the trajectory wave function will have this easing symmetry breaking or spin glass order, and that's traditionally diagonalized by the like probed by this old quote-unquote order parameter, this xi xj, evaluated on the trajectory wave function squared and then average over all the sample. So this type of the order parameter, and again that we propose this replica or modified version of that. So the signature of the spin glass order is that this order parameter will scale linearly in the total system size. But if you're in the disorder phase, this order will scale basically constant or almost zero as a function of system size. And you do see here that we're pretty deep in the phase. And then using our protocol, we do see that when the ZI measurement rate is low, so the XX measurement rate is high, by the exact simulation does show that they should be in the spin glass phase. And then our verification protocol, which are these solid and square symbols, that they also can show this order. Yeah. So actually, I think I'm basically out of time, and then this is like the last slide. So we can probably just step back and discuss a little bit. So we propose to overcome this post-election challenge. So, and then basically the way that we do is that instead of looking at the final wave function, we actually use the data of this mid-circuit measurement outcome. So what we are trying to trade, the trade-off here is that we're trying to trade this exponential sample complexity from your quantum device. So again, that one of the exponential coming from you need to do the tomography. So usually that the complexity scales exponentially in the number of qubits. Another is actually coming from this post-election to get the same state that you need some sample size that's probably exponentially in the number of the measurement. And so which is actually exponential in the number of qubits and the depth of the circuit. So right now what we do the trade-off is that instead of the sample complexity in the quantum device, we have this classical post-processing resource. So the question is like how much we gain. Of course that we do overcome the post-election, but how much classical resource we need to pay. And of course that this could be like a algorithmic dependence. So especially what we mentioned is that we use this matrix product state and matrix product operator algorithm. So the usual expectation is that the resource you need to use in this type of the algorithm kind of depending on the amount of the entanglement in your quantum wave function that you want to simulate. So and then from our calculation result, and also just by some guess that we kind of expected that, or maybe if we are trying to probe the system in the volume law phase, this post-processing calculation might actually still need exponential resource in terms of the system size, but you do gain an exponential gain coming. So it doesn't depend on the depth anymore. It might only depend on the number of qubits. But we have it might actually shine that it might have a good edge that if the system is in the area law phase, and then the MPS, this type of algorithm might only need a polynomial resource. And again, that this is like a possibly algorithm dependent. So maybe there are different algorithms to calculate this post-processing W function. For instance, there could be some Monte Carlo algorithm that could have an edge in the area law phase. And something that we are trying is that can we actually use some machine learning to learn this post-processing W function and to speed up this post-processing process. And also there are actually still some other things that we haven't really explored, like say how robust this quote-unquote verification protocol against the error. Say we kind of expect the gate error will probably not be a problem because we average over all the gates. So how precise you do it probably doesn't matter. But we don't know what's the effect of the readout error or this typical decoherence error or incoherent error if we don't know the location. Yeah. And finally, I want to mention, I don't have time to explain about this point yet, and this is like a vague wishful thinking, is that could this be a type of problem for you to hunt for a problem that has a so-called verifiable quantum advantage? Yeah. And with that, thank you for your attention.
Great. Thank you so much for that talk there. I don't see anything in the chat, but I do have one question. So, I mean, of course, no method, there's no free lunch with any method really. But the limits you said before were 8 qubits for a full system on the IBM device, 14 with short depth. Do you have any guess, any estimate for what you could do with like reasonable access to a quantum computer and reasonable access to like a university-sized cluster, let's say?
Right. So here that I would say if I assume there's no error, so meaning that I don't want to pay any resource for say error mitigation or whatnot. So all this calculation, the real bottleneck is my classical computer trying to simulate the real quantum device. Yeah. Mm-hmm. So if that's not a constraint, meaning that I can really have a quantum device with a simple outcome, the bottleneck will become the classical post-processing. And right now for the calculation that I have, I would say I can comfortably do the post-processing if it's in the volume law phase for maybe 30 qubits. One could probably optimize the algorithm to push to 40. Yeah. So yeah, but to get more than probably only area law phase is okay. Volume law phase might be challenging to go beyond that number. Yeah.
Got it. Yeah. Thank you.
Yeah, no problem.
Well. All right. Well, thanks so much again for coming in, Jacob. And of course, a big thanks to the audience here for tuning in. Just like this video, subscribe to the Qiskit YouTube channel, and we'll see you soon. Thanks, everyone.
Thanks, everyone.